Section: Introduction. In this section, we explore the concept of tokenization, which is fundamental to natural language processing, NLP, and serves as the initial step for using a language model, LM. When we have a string of characters, a tokenizer transforms it into a string of subwords. Language models are trained to predict distributions over these subword strings, without ever seeing the original character strings. Despite its importance, there is still much we do not understand about tokenization. For example, we are unsure what qualities make a tokenizer effective and what characteristics the resulting subwords should have to support language modeling. If we could identify these qualities, we could create an objective function to evaluate different tokenizers. Another question we face is how to efficiently find a tokenizer that maximizes this objective function. For instance, byte pair encoding, BPE, is a method that greedily seeks to maximize text compression, while unigram LM is a heuristic approach aimed at maximizing the log probability of the tokenized text. However, both methods are approximations and may not yield the optimal tokenizer according to their respective objectives. This leads us to question whether it is even feasible to find optimal tokenizers efficiently. In our paper, we address this question by demonstrating that several variations of the tokenization problem are nitrogen monophosphide complete, particularly focusing on the task of maximizing text compression. We define the tokenization problem as finding a tokenizer that compresses a dataset to a specified maximum number of symbols. Previous research has applied different constraints on tokenizer definitions, but we consider two main types: direct tokenization, where we select a vocabulary directly to represent the text, and bottom-up tokenization, where we achieve the desired compression through a series of merge operations on the input text. We prove that both types of tokenization problems, along with some of their variants, are nitrogen monophosphide hard by reducing them from the max2 satisfiability problem. This suggests that finding efficient algorithms for optimal tokenizers is unlikely, and we should instead focus on approximate methods like BPE or unigram LM. When it comes to choosing a tokenizer, theoretically, the choice should not affect the quality of the language model. We can derive word-level or character-level distributions from any subword-level language model. However, in practice, a poor tokenizer can negatively impact downstream applications. For example, performing arithmetic tasks can be challenging due to how numbers are split into subwords. Even advanced models struggle with simple counting tasks, highlighting the importance of selecting an effective tokenizer. Ideally, we would select the tokenizer that maximizes performance in downstream language modeling. Unfortunately, measuring this performance directly requires fully training a model, which is computationally impractical. Instead, we optimize proxy objectives that are believed to correlate with downstream performance, such as unigram log probability, Rainey efficiency, and compression. In this paper, we focus on compression, defining our objective function as the negative length of the subword string. Improved compression can lead to more efficient training and inference, better downstream performance, and fairer treatment of multilingual data. We define a tokenizer as a three-part structure consisting of a vocabulary, a tokenization function, and a detokenization function. To clarify these terms, we first establish some notation. A character string is a sequence of characters from a given alphabet, and a dataset consists of multiple character strings. A subword represents a non-empty character string, and a subword string is a sequence of subwords that together represent a character string. With this notation, we can define the components of our tokenizer. The vocabulary is a set of subwords that includes the alphabet, and its size is the sum of the alphabet size and the number of additional subwords. The detokenization function takes a subword string and outputs the corresponding character string by concatenating the subwords. The tokenization function maps character strings to subword strings, ensuring that the original character string and the tokenized subword string are equivalent. There are various ways to define tokenization functions, but we focus on two main approaches: direct and bottom-up tokenization. We will elaborate on these definitions next. Section Summary. In this section, we explore the critical role of tokenization in natural language processing, highlighting the challenges in defining effective tokenizers and the nitrogen monophosphide completeness of finding optimal tokenizers for text compression. We also discuss how the choice of tokenizer can impact downstream language model performance and propose focusing on compression as a proxy objective for selecting a good tokenizer. Section: Direct Tokenization Functions. In this section, we discuss direct tokenization functions. In direct tokenization, we replace a character string directly with an optimal subword string. To do this, we first need to define what optimal means, which we achieve through an objective function that gives a score for a subword string. With a chosen vocabulary, the direct tokenization function encodes a character string into the best subword string from that vocabulary. We define our tokenization function as equivalent to this direct tokenization process. Different choices of the objective function can lead to various methods, such as unigram LM or pathpiece. However, we note that this function is generally not easy to compute. Our focus is on tokenizers that use compression as their goal, where the objective function is the negative length of the subwords. In this case, we can compute the direct tokenization function efficiently. Next, we explore bottom-up tokenization functions. Here, we start with a set of character strings and merge their symbols one pair at a time. We define a merge as a pair of subwords and create a merge function that replaces occurrences of one subword followed by another with their combined form. For example, if we have the subwords wo and are, merging them gives us war. We can apply a sequence of merges to compress a character string. The bottom-up tokenizers are defined based on this merging process, and the size of the vocabulary is determined by the number of merges. Finally, we aim to prove the nitrogen monophosphide completeness of tokenization. To do this, we will reduce a nitrogen monophosphide hard problem to tokenization in polynomial time, specifically using the maximum 2 satisfiability problem, max2 SAT. We define a set of variables, each assigned a true or false value, and a set of clauses made up of these variables or their negations. The max2 SAT decision problem involves determining if there is an assignment that satisfies a minimum number of clauses. We illustrate this with an example of variables and clauses, showing how certain assignments can satisfy the maximum number of clauses. Section Summary. In this section, we describe two tokenization methods: direct tokenization, which replaces character strings with optimal subword strings based on a defined objective function, and bottom-up tokenization, which merges character strings incrementally. We also introduce the maximum 2 satisfiability problem to demonstrate the nitrogen monophosphide completeness of tokenization by reducing a nitrogen monophosphide hard problem to it. Section: Finding an optimal direct tokenizer. In this section, we focus on finding an optimal tokenizer. We can achieve this by either selecting its vocabulary in direct tokenization or its merge sequence in bottom-up tokenization. Here, we concentrate on direct tokenization, defining its optimization and decision problems, and we will demonstrate that it is nitrogen monophosphide complete. The optimization problem involves a dataset and a vocabulary size. Our goal is to find a vocabulary that maximally compresses the dataset. Similarly, the decision problem asks whether there exists a vocabulary that can compress the dataset to a specified maximum number of symbols. We denote a function that checks this as mintalk, which returns true if the problem can be satisfied and false otherwise. If the size of the dataset is less than or equal to the vocabulary size, the solution is straightforward, as we can include all characters in the vocabulary. Next, we state our theorem. The direct tokenization decision problem is nitrogen monophosphide complete. A decision problem is nitrogen monophosphide complete if it is in NP and is nitrogen monophosphide hard. We will prove these conditions in the following sections. To show that direct tokenization is in NP, we note that if we have a certificate of polynomial length, we can verify it in polynomial time. In our case, the certificate is a vocabulary that allows the dataset to be compressed to a certain number of symbols. Verifying this involves checking a sum, which can be done efficiently if the function we use runs in polynomial time. Now, we demonstrate that direct tokenization is nitrogen monophosphide hard by reducing the max2 SAT problem to our tokenization decision problem. We define an alphabet and construct sets of strings based on the max2 SAT problem. We then create a dataset and set parameters for vocabulary size and maximum symbols. Our reduction must ensure that a max2 SAT problem is satisfiable if and only if the corresponding tokenization problem is also satisfiable. We prove the forward direction of this relationship by fixing a satisfying solution to the max2 SAT problem and showing how it leads to a valid vocabulary for the tokenization problem. We also prove the backward direction, demonstrating that if a tokenizer can compress the strings appropriately, it implies a satisfying assignment for the original max2 SAT problem. With these proofs, we conclude that the direct tokenization decision problem is indeed nitrogen monophosphide hard, as the reduction runs in polynomial time, and the max2 SAT problem is nitrogen monophosphide hard. Section Summary. In this section, we focus on finding an optimal direct tokenizer by defining and proving the nitrogen monophosphide completeness of its optimization and decision problems, which involve selecting a vocabulary that maximally compresses a given dataset. We demonstrate that the direct tokenization decision problem is nitrogen monophosphide complete through a reduction from the max2 SAT problem, establishing both its membership in NP and its nitrogen monophosphide hardness. Section. Finding optimal bottom-up tokenizers. In this section, we focus on bottom-up tokenization. We define both the optimization and decision problems related to it, and we demonstrate that it is nitrogen monophosphide complete. First, we outline the optimization problem. Given a dataset and a specific vocabulary size, our goal is to find a sequence of merges that compresses the dataset as much as possible. This is similar to the direct tokenization problem, but instead of finding a vocabulary, we are looking for a merge sequence. Next, we define the decision problem. Here, we need to determine if there exists a merge sequence that can compress the dataset to a specified maximum number of symbols. We will show that bottom-up tokenizers are nitrogen monophosphide complete. To prove this, we first establish that the decision problem is in NP. We can verify a solution, which is the merge sequence, as a certificate. This certificate has a polynomial length and can be checked in polynomial time. To verify it, we compute a specific sum, which we can do efficiently. We also show that if the vocabulary size exceeds the total number of characters in the dataset, we can easily compress the dataset to a single symbol. Thus, checking if the dataset can be compressed to a certain size is straightforward. If the vocabulary size is limited by the dataset size, the certificate remains polynomial in length, and verifying it involves computing another sum, which requires a number of calls to a function that operates in polynomial time. Now, we turn to the nitrogen monophosphide hardness of bottom-up tokenization. We use a reduction from the max2 SAT problem to demonstrate this. We define an alphabet and construct several sets of strings to form our dataset, along with specific vocabulary size and maximum symbols. We follow a structured proof to show that if we have a satisfying solution to the max2 SAT problem, we can create a corresponding merge sequence for the tokenization problem. This sequence will ensure that the dataset is compressed to the required size. Finally, we prove the reverse direction of our reduction, showing that if we can compress the dataset as required, it implies a satisfying assignment for the max2 SAT problem. Thus, we conclude that bottom-up tokenization is nitrogen monophosphide hard, as the reduction runs in polynomial time, and max2 SAT is known to be nitrogen monophosphide hard. Section Summary. In this section, we explore bottom-up tokenization, defining its optimization and decision problems, and proving both are nitrogen monophosphide complete. We demonstrate that the decision problem can be verified in polynomial time and establish its nitrogen monophosphide hardness through a reduction from the max2 SAT problem. Section. Other definitions of tokenization. In this section, we expand our discussion to explore different variations of the tokenization problems we previously addressed. First, we consider deduplicated datasets. Our definitions of direct and bottom-up tokenization allow for datasets to have repeated entries. However, in natural language processing, NLP, it is common to remove duplicates from datasets. To adapt our reductions for deduplicated datasets, we can simply add a unique character to each string in the repeated datasets and adjust the target compression size accordingly. These new characters will not be included in the optimal tokenizer solutions, so our previous proofs still hold, with the understanding that each dataset will require additional symbols after compression. Next, we look at the case of a single long string. While we previously focused on tokenizers trained on datasets, compression typically deals with a single long string as input. We can see that direct tokenization is not a complex problem when the input is a single long string, as including it in the vocabulary achieves optimal compression. However, bottom-up tokenization remains a complex problem even with a single string. We can demonstrate this by appending a unique character to each string in the dataset before concatenating them. Similar to the deduplicated case, these characters will act as virtual delimiters and will not impact our proofs, aside from increasing the target compression size. We also consider a hybrid approach that combines direct and bottom-up tokenization. In this case, we find a merge sequence that allows us to extract a vocabulary that optimally compresses a dataset using the direct tokenization function. We can prove the complexity of this hybrid tokenization by applying a similar strategy as before, as our previous proof did not depend on the order of merges. Finally, we discuss the connection between tokenization and compression. The tokenization variants we examine aim to reduce the size of an input by leveraging repetitive elements, which is similar to dictionary compression. The popular BPE algorithm, initially a compression method, has been adapted for tokenization in NLP. Previous research has also explored the theoretical aspects of compression achieved by tokenizers, particularly in bottom-up tokenization. We can illustrate the similarities and differences between tokenizers and compressors using straight-line programs, SLPs. An SLP describes a grammar that can uniquely generate a string. Finding the smallest SLP for a given string is a complex problem. SLPs in Chomsky normal form relate closely to bottom-up tokenization, while those not in this form relate to direct tokenization. This comparison highlights two key differences. First, tokenizers focus on reducing the size of the tokenized text, while compressors also consider the size of the compression information. Second, tokenizers and compressors have different optimization goals. Compression algorithms aim for maximum compression, while tokenization algorithms work within a set vocabulary size limit.